Jai Hind, dear students. Today I am going to take a topic in this subject, computer organization and architecture. Today's topic is virtual memories and implementation. Virtual memory plays a very important role in computer world because large size processes are coming which are executing in the process and they cannot be accommodated in the main memory. While there is another need of virtual memory is that apart from large size process, we have multiple processes running in the system. So all the process cannot be accommodated in main memory. So here comes the role of virtual memories. So let's start the concept of virtual memory. We know the challenges in the design of computer system, and one of the challenge is that we require a large memory size. And we have already discussed in the previous lecture that to have the fast memory we use concept of cache memory. So what is the architectural solution for the large memory? Virtual memory is the solution for the large memory. The architectural solution increases the effective size of the main memory that user sees, and the cache memory provides the speed up, and virtual memory provides the space or the large memory. So effectively the memory system looks large to the user, and user wish to execute a large size program, or the user wish to execute many programs that is larger than the size of main memory. So here the virtual memory plays a very important role. So we came to know that the virtual memory plays an important role to provide a large space for the processes and program run by the user. We know that addressable memory space depend upon the number of address bits in a computer. For example, a 32-bit address, we have a total address space of 4 gigabytes. How it is possible? So 2 raised to power 32 address space are there. So this will come out to be 2 raised to power 2 into 2 raised to power 30. So 2 raised to power 30 is 1 giga. So this will result into 4 gigabyte address space. So physical memory of a computer is generally not very large, and we do not have that much address space where a big program can come. So typically in commodity systems, the RAM size or the memory size is 1 gigabytes, but nowadays the advanced concepts are possible to have higher capacity of memories. So in earlier days the size was very small and it is in gigabytes, in around 1 gigabyte. So the processes that cannot execute in the main memory has to wait till the older processes or the previous process has executed. So this will create a problem of less memory in the system, and large program size cannot execute, and even many programs cannot execute. So large program cannot fit this small space. But later on, nowadays, even if we have a larger size of main memory like 8 GB or 16 GB in the commercial systems, the need of executing program is growing on with the larger size, and many programs are running together. So, this space is still a very small space to execute the program. So, large program that cannot fit, how they can be executed in the main memory. So, the pieces of program must be transferred from main memory to secondary storage before they can be executed. The program is actually stored in the secondary storage, and a piece of a program is brought to the main memory to execute it part by part. Now, if we are doing this, there will be a extra effort required to move the piece of a program to the main memory, and more number of pieces, more time we have to transfer, and that will create a overhead. So, is it possible to have an improvement in this scenario, that this transfer takes place in very fast way? So, virtual memory incorporates some solutions for these type of problems. When a new piece of a program is transferred to the main memory and the memory is full, so what we will do? We will move some piece in the main memory, and it will be moved to the back to the storage. So, it is similar to what we have studied in the cache memory. If the cache line is full or the cache memory mapped location is full, we can bring a new block only when the previous block which is existing in the cache memory is replaced. So, there is similar technique used in the virtual memory when the main memory is full. So, who performs this particular task? The operating system automatically transfers data between the main memory and the secondary storage in the background. Okay, so application programmer need not to be worry about this transfer. Okay, so at the background, the operating system takes place the charge, and this will happen without disturbing the programmer. So, application programmer does not need to be aware about the limitations imposed by available physical memory, and they can create a program larger than the size of main memory, or many programs can be running together, because the program is executed in the main memory piece by piece, and the one piece is brought in the main memory, and if the main memory is full of pieces, the one particular piece will be removed and the new piece will brought into the second main memory from the secondary storage. Techniques that automatically move program and data between the main memory and secondary storage when they are required for execution are called as virtual memory technique. So, this particular technique is named as virtual memory technique. So, program and process reference and instructions or data are independent of size of main memory. Whenever a user writes a program, they never think about the hardware specification, what is the memory size. Okay, so programs are written independent of that. So, processor issues a binary instructions and data to refer that particular program in the user process. So, what virtual address do? Virtual address translated into a physical address by a combination of hardware and software subsystem available in the computing system. So, software subsystem is part of operating system, and a hardware subsystem is a part of CPU itself. So, virtual address refers to part of a program that is currently in the main memory, and it is accessed immediately. If address refers to part of program that is not currently in the main memory, it is first transferred to the main memory before it can be used. So, the pieces of the program is not in the main memory is brought to the main memory whenever required, and that will be done through the virtual memory technique. Now, if we see this diagram, whenever a processor requests any address to refer a data or a instruction, it will go to a special unit that is called as memory management unit. So, this memory management unit translates the virtual address into the physical address. Okay. So, output of this memory unit management unit is physical address. If the desired data or instruction are in the main memory, they are fetched as we have described previously, and if the desired data or instruction are not in the main memory, they must be transferred from the secondary storage to the main memory. So, MMU causes the operating system to bring the data from the secondary storage into the main memory. So, this will instruct the operating system that the virtual translation of address, virtual address being translated in main memory as a physical address is not available, and the operating system will intervene and bring that particular data to the main memory if it is not available. So, assume that if a program and data are composed of fixed length units called pages. So, we have told that there is a piece of a program. So, this piece of program is now known as page. So, it is of fixed size. So, if there is a virtual memory space, okay, it is divided into small units, and they are called as page 1, page 2 and so on, page n. So, these are pages of particular program, or you can say pieces of the program. A page consists of block of words that occupy contiguous location in the memory. So, this particular page is a contiguous location. It is a contiguous location of bytes, byte 0 to byte n minus 1, contiguous location, and they will go into the main memory at in a sequence. Okay. So, that is why it is a contiguous location in the main memory. This page is a basic unit of information that is transferred between secondary storage to the main memory. Now, what is the common size of these pages? We know that usually when we talk about the cache memory, the block size is around 16 to 32 or 64 bytes. But what is the size of page? The size of page ranges from 2 kilobytes to 16 kilobytes. So, now consider 2 kilobytes. Okay. How much number of bytes is there in 2 kilobytes in terms of counts? So, we can say that 2k is basically 2 raised to power 10, and we know that 2 raised to power 10 is 1024. So, roughly it is 2000 bytes in the one page. Okay. So, the block size is very small with respect to the page size. So, in a page there are ranging from 2000 to there are 32,000 bytes in the page. Now, page should not be very small, because the access time to secondary storage device is much larger than the main memory. What will happen if the page size is very small? We have to go to the secondary storage to bring that page again and again, and if it is too large, the portion of page may not be used and it will occupy valuable space in the main memory. So, page size is very large, the amount of utilization of the page will be small, the rest of the space is not having any data or instruction. So, there is a trade off between the size of page, and that will be compromised in the two optimization. One is that time will be more required for bringing the pieces or pages of program to and fro from the main memory to secondary storage. Secondly, there is underutilization of page if it is too large. So, that should be taken care depending upon the requirement of the programming user, and that can be changed in the operating system environment variable. So, if we consider the concept with the cache memory is somewhat similar to the virtual memory. So, we know that the purpose of cache memory is to speed up or reduce the time of access of data from the memory. So, similarly, virtual memory is used to provide a large space for storage of large program. So, this time is basically to bridge the gap of speed between processor and the main memory, and it is implemented with hardware only. But to have a large space, this will bridge the gap between the main memory and the secondary storage. Okay. So, we do not require to bring data from the secondary storage, data is available in the main memory. Okay. And it is implemented using both software as well as hardware. So, partly software, partly hardware. Each virtual address space generated by processor is interpreted as a virtual page number. Okay. So, we already know that in the previous slide we told that the processor generates a virtual address. So, the virtual address is to be looked as a higher order bits of this virtual address. So, a virtual address is divided into two parts. So, the virtual address is generated by processor is interpreted as two parts, virtual page number, okay, and the second part, the lower order bits, is known as offset. Okay. Offset is the particular byte position in a particular page. So, information about the main memory location for each page is kept in a table, which is very important for the process to refer again a new page. So, for every process which is being currently running, we maintain a information of the page that is to be used for that program, and that is kept in the page table. So, there is a page table, okay, and it maintains information about the virtual pages, okay, available in the main memory, virtual page 1, virtual page 2, virtual page 3, virtual page, so on, and there will be the main memory location, that is virtual page frame location of particular page in the main memory. So, every process has one page table which maintains the virtual page available in the main memory, and that will be important when we are referring a particular page again and again. So, main memory address where the page is stored, okay, and it stores the current status of the page also, that is how we are accessing this page. Okay. So, area of the main memory that holds page is called as page frame. Okay. So, the virtual memory and the main memory has two different terminologies. So, in virtual memory, okay, every fixed size location is called as page number, and when it moves to a particular main memory location, okay, that is called as virtual page frame. So, basically this table contains the mapping between the where this particular page number residing in which particular page frame. Okay. So, yes, we know about the location of this table, and the location of this table is referred by the page table base register corresponding to a process. So, this starting address is also required, so that we can refer it again and again and identify the particular offset corresponding page virtual page number within the page table. So, virtual page number generated by processor is added to the contents of the page table register. So, whenever a virtual page number is generated by the CPU. Okay. So, the process by the processor, it is added to the contents of page table base register. So, what will happen? VPN will be added with the contents of page table base register. So, the particular entry will be available in the table. So, this will provide the address of corresponding entry in the page table. As soon as VPN is added with PTBR, it will give the corresponding address entry in the page table. The content of this location is page table given in the starting of the address of the page if the page is currently in the main memory. So, this location gives the starting address of the page if the page is currently in the main memory. Only it is available. If it is not available, it will show that the entry is not there. Okay. So, how it looks like that? You can simply see in this diagram. This processor generates the virtual address, and we already know the virtual address is divided into two parts: virtual page number and the offset. Okay. So, the virtual page number goes to a hardware module that adds the page table address, and that will result into in location in the page table. Okay. So, PTBR plus virtual page number provides the entry of page in the page table. So, this particular virtual address is available in a particular location virtual page frame, and it is entered in this particular page table, and that can be identified by adding this page table PBTR starting address to the virtual page number, and that will result into the virtual page frame number. Now, this virtual page frame number is concatenated with the offset that is directly taken from the virtual page address, and this will give the physical address in the main memory. Now, there is some starting data in each entry, and that is basically the control information or control bits about the page frame, the restriction provided by the operating system to access that particular data in that particular page frame. So, page table entry for page also includes the control bits that we have already told, and which describes the status of page while it is in main memory. So, usually one bit in this control is talking about the validity of the page, which indicates the page is actually loaded into main memory and allows operating system to invalidate the page without actually removing it. The purpose is very simple, that whenever if it is not valid page, so we do not require to move the content of page to the virtual space, simply we have to overwrite it. So, this will help in extra overhead for moving the data from the main memory to the virtual memory in the hard disk. So, this one bit indicates whether the page has been modified during its residency in the main memory. If it is modified, certainly we have to move it to the virtual address space if it is to be removed. Okay. So, this bit determines whether the page should be written back to the disk when it is removed from the main memory, and similar to dirty bit concept that we have studied in the cache memory. Okay. So, if page is dirty, so it is similar as it indicates that it has been updated, it has been modified. Now, other control bits are also there for restrictions to be imposed on the page, because in the main memory multiple processes are running. So, if a particular page is to be accessed for reading or writing, or we can modify it or not, are also available in this control bit information. So, important control bit is that whether it is modified or not, so that overhead to move the pages from main memory to the virtual memory is reduced. That is very important thing. So, where should be the page table be located, and this page table is to be located somewhere on the main memory or somewhere on some specialized hardware. So, the page table is basically a part of memory management unit, okay, and it is located ideally in MMU, but page table is quite large, okay. So, the number of page frame available in the main memory, that many size of records are available in the page table. So, we can implement that page table into MMU, but we cannot put all the page table entry in the chip because it is quite large, around it will be in the lakhs. So, we cannot keep the, lakhs of entries, 40 to 80 lakhs of entries on a chip. Okay. So, where then we keep this, we keep it in the main memory initially starting, but we know that if we are keeping it in the main memory, every time we have to refer any address, we have to first refer the main memory, okay, the first reference to the memory, and after we have found that the data is available because the page table is saying the data is available, so then we have to go to the main memory again for the actual address location. So, there are two times access to the memory. So, this will be quite slow. So, actually the copy of small portion of the page table is kept in the memory management unit, okay. So, portion of page table entries are kept into the memory management unit, and which particular portion, the portion of table which is recently being accessed. So, as we have done in the cache management, least recent use of the blocks are removed. So, likewise, the most recent page references in the page table are brought into the this small hardware, so that we can easily refer it. So, small cache, and that particular cache is called as translation look aside buffer, okay, and it is a part of MMU. So, as similar is in the cache, the page table entry for a page includes address of the page frame that we have already discussed, and some control bits same as that we have discussed in the page table, and the TLB must hold a virtual page number of each page, so that we can search there whether it is available or not. So, like we search the block is available in the cache or not. So, virtual page number is stored here, and corresponding page frame number is stored here, and this is searched in parallel, like we search for the particular block is available in the cache through tag comparison, and the tag comparison is done in parallel through, that is why it is very costly. So, content addressable memory is used. So, you can see multiple arrows are going there, and if this virtual page number is present, it will give answer yes, it is available, then it is hit, if it is not available, it is miss. So, dear students, this is a very important concept of cache memory main memory management through virtual memories, that will speed up the process of referring a particular page into the processor, and this will improve the speed of execution, because the data is available in the page table for a particular page, and it is referenced from this page table, and that will tell about the particular page frame whether the data is available or not. So, in Jai Hind students, today we have learned the concept of virtual memory translations, and how it is implemented using the page table, and the concept of page table, that is to be stored directly on the main memory, or we have to take a part of that page table into the memory management unit as a small cache. Thank you and Jai Hind.